Okay, next up is a queue, and we learned about a stack. A stack was a last in, first out container. A queue is a first in, first out container. And queues are particularly useful when we need to buffer some data. So imagine, a printer might be able to print 80 characters per second, but the computer that's talking to the printer through the network may be able to produce 8,000 characters per second. Okay, so the remaining characters are queued or buffered in a queue. Okay, so you can think of a queue kind of like a pipe. So there's a front and a rear. Okay, and when we insert elements, we're going to insert elements at the rear of the queue. And then when we remove them, we're going to remove them from the front of the queue. And the data is buffered inside the queue until they can be used. Okay. So let's take a look here. So here's our queue. It's got, again, the front and the rear. And the way we add to a queue is we call this method enqueue. Okay, so if we were to look at the interface to the queue, there's enqueue, that's kind of equivalent to putting something on the queue, and dequeue will remove something from the queue. And again, we're going to pass in the data that we want to add to the queue by reference so that we don't have to make a copy. And we're going to make that constant data, so elem shouldn't change when we're enqueuing it. Dequeue is going to take a T reference. This is so that we can get back a value, whatever is at the front of the queue. Okay, so I'm just going to enqueue the letters of my name here. So when we enqueue M, okay, we're going to go to the rear and stick the M character in there, and then enqueue A, enqueue R, enqueue K. You'll see the pipe is now full with the data that's been buffered. Okay. Next, we would want to dequeue. So here's where we kind of left off here with our full queue. Now when we dequeue, we're always going to remove from the front. So the first dequeue will give us the value M, then A, then R, then K, and the queue will then be empty. Okay, so there's a couple different ways to implement a queue, just like there was the stack. So we could have a linked list based queue. And if you have a linked list with both a head and a tail, you have the ability to add and remove from the front or the rear. And if you have a linked list like that, well then your queue will just basically reuse that entirely. Okay, so the way that would look is something like this. So we start out with a totally empty linked list that has both a head and a tail. And then we're going to insert at the rear. So we're going to go to what the tail points to, and that's where our new nodes are going to go. So we have the M, and then when we insert the A at the rear, again, we're going to go to the tail. We're going to add the new node there, the R and the K. And then when we would want to dequeue, okay, what we would do is we would remove from the front. So after dequeuing this full linked list, we'd get the M value back, and our linked list would look like that. And then we get A, R, and K, and we'd end up with a totally empty linked list. Okay, we talked about the real-time requirements, or we talked about real-time requirements when we were talking about a stack, and the fact that an unknown length of time to allocate a node in a real-time system can be problematic. Okay, the same is obviously true for queues. So occasionally you might find that you can't create a linked list based queue, and instead you would want to create an array based queue. An array based queue supports rapid insert and removal without the overhead of dynamic memory allocation. With an array based queue, we keep track of the front of the queue and the rear of the queue with an index value. So we might have this index called front, which maybe starts at position 0, and rear, will also start at position 0. Okay, to NQ, what you do is you add the piece of data at the index of the rear, and then you increase the rear by 1. So again, going through the enqueuing of the letters of my name, since rear starts at position 0, to NQ we would put the M there, and then rear would get increased. And then when we NQ A, we'd put the A there, and we increase rear. We'll do the R, put the R there and increase rear. And finally the K would go in this position here, and the rear would be increased by 1. To DQ, you remove from the index of the front, and then move the front up by 1. So again, the front started at position 0. If we were going to DQ this full Q here, we would get the M back and then push front forward. And our Q would look like this after our first DQ. Then the second DQ, we'd remove A and push front forward. Next DQ, we'd remove R and push front forward. Our last DQ would remove K and push front forward. And now notice what happens here. We have a totally empty array here, but obviously we can't use our same algorithm to just increase rear and front. We're already beyond the bounds of this array. Okay, so what do we do here? Looks like after we DQ'd 4 times, we're kind of stuck because we can't reuse any of those empty spaces. Well, this is true only if we think about an array as being this linear chunk of data. There's another way to think about this. We could say, well, you know, we can think of the array as being kind of a circular shape. Okay. So let's try and imagine that. So imagine we have this linear array, and we just decided to just imagine it was kind of circular, meaning that once we got to the end here at position 3 and we wanted to move forward, instead of increasing it by 1, what if we wrapped around back to 0? Okay, so let's go through the process then of NQ. Okay, so we have this circular buffer now where, again, we have a front and a rear, and front and rear start at position 0. When we NQ the letter M, we go to the index at the rear, which was 0, and we store the value there. And then we push the rear forward, so now it's at position 1. Our next NQ, we would put the A here and push the rear forward, okay, and so on. And now when we have a totally full queue, our rear and front are both, because we pushed them forward, they are now both at position 0. Now if we start dequeuing, again, we're going to go to what the front points to, that's position 0, and start removing things. And actually the front would be here. Okay. And then our next DQ, the front would be pushed forward, and so on, until now when we have the empty queue. Front and rear are both at position 0. We could start pushing NQing and DQing again, and just circling around ourselves. Okay, so a circular array works only if we can when we get to the end of the array, we wrap back around to 0. So how we would do that is there's a couple different ways we could do that. We could kind of implement this method here to increase the index. So we could take the index plus 1 and then mod it by the array size, and that would be our new index. So we could have maybe a push forward method that would maybe take an index value and just do this little bit of math. So what you'll see here are some examples of what would happen if we pushed forward 0. Well, 0 plus 1 mod 4 is 1. 1 plus 1 mod 4 is 2. 2 plus 1 mod 4 is 3. All of that's pretty uninteresting. The interesting one is when we get to the last index value, 3. 3 plus 1 is 4. 4 mod 4 is 0. So we get the sequence 1, 2, 3, 0, 1, 2, 3, 0. And basically we we kind of wrap around and get that circular behavior. Of course, there's another way to do that with maybe a little bit more code, a few more lines of code. That just uses an if. So if the index plus 1 is ever equal to the array size, well, that means we've gotten to the end and we can wrap around the index to 0. Otherwise, we would just add 1 to the index. I kind of prefer this. I think it's a little bit more readable than the statement with the mod, but I guess that's just a personal opinion. Okay, so that's a queue. It's a first in, first out container, similar to a stack. So stacks and queues are very much related. The only difference is the way that we get things back when we pull things out of the queue.